On average, lightning strikes occur close to 10 million times a day. And for lightning bolts, a plane flying thousands of feet in the air is a natural target. We took an exclusive look inside the Boeing Lightning Lab to see how they manage it. From the inside of a plane going through clouds full of lightning, the scene can look scary. But despite the looks, a plane is safe when hit by lightning. Let's have a look at why that is. Let's kick off our exploration with the question, how does lightning work? In a storm cloud, countless tiny ice particles are moving around, colliding with each other. These collisions cause a separation of electric charges. Positively charged ice crystals move up towards the top of the storm cloud, while heavier, negatively charged particles sink towards the bottom. This separation creates an electric field within the cloud. As the electric field intensifies, it also affects the charges on the ground below, pulling positive charges closer. When the electric field becomes too strong, the air molecules begin to break down, and we get a conductive path, a channel for the electricity to move through from the cloud to the ground. This is what we call a lightning strike, a giant spark of electricity equal to about 100 million to 1 billion volts that neutralizes the difference in charge. But it's not just the ground that lightning strikes. It can also strike between clouds, within a single cloud, or even objects in the air, like planes. A lightning bolt can heat the air it passes through to 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. This rapid heating and cooling causes the air to expand quickly, leading to a shock wave we hear as thunder. And yet, modern airplanes continue to fly through such conditions safely. Let's look at what happens when these high-voltage natural fireworks meet a man-made marvel soaring high in the sky. You may assume that when lightning strikes an object in midair, such as an airplane, the outcome should be catastrophic. However, airplanes are incredibly resilient in the face of lightning. But why is this so? Firstly, we need to understand that an airplane is not an ideal point for lightning to discharge. As explained by the Boeing Lightning Lab lead engineer, Stephen Henning.
It depends on the amount of voltage you got potential and whether or not all of it is able to bleed off into that one spot at that point.
When an airplane is in flight, it's not grounded. That means the lightning is not discharging its full potential to the ground through the plane. Instead, what happens when lightning strikes an airplane is similar to the airplane catching the lightning. The airplane, primarily being made of conductive materials like aluminum, allows the electric charge of the lightning to travel along the plane's skin and exit back into the air. This path is known as a swept stroke. The plane is like a bird flying through a waterfall, getting wet but emerging relatively unscathed on the other side. To visualize this, picture an airplane cruising smoothly at 30,000 feet. Suddenly, a bright flash envelops the plane. It's been hit by lightning. Inside, the passengers might see a bright light and hear a loud sound, but often they don't notice a thing. The plane continues its journey unperturbed. Now, the engineering of airplanes to protect against lightning strikes is not accidental. It is a product of intentional design and robust testing. The airplane skin, made of conductive material, creates what is known as a Faraday cage. This shields the interior of the plane from external electric fields and largely neutralizes the effect of the lightning strike. That being said, lightning strikes can still cause minor external damage to planes, such as burn marks or minor erosion on the surface. In rare cases, they can affect the plane's electronic systems. But these are exceptions rather than the norm. A critical piece of information shared by our expert throws light on this concept.
In this case, we're talking about the damage you'll see on the plane as it's flying and as it's going out. Damage over time is what causes this is where you start getting more issues. That's what we want to protect. We want to make sure that our safety is going to protect the plane from those cases.
Now, you might think that since planes are virtually immune to lightning, it is perfectly safe to go through storms and never try to avoid them. But let's see how pilots interact with these dramatic displays of natural power. Despite understanding the inherent safety of modern aircraft against lightning, pilots still take precautions to avoid these atmospheric phenomena. But why? Well, the answer is twofold. First, lightning strikes can affect a plane's external sensors, like pitot tubes, which measure airspeed, and this can be a problem for pilots. Also, multiple lightning hits over time can lead to maintenance issues, and therefore it's in the airline's best interest to minimize exposure. Second, the encounter with a lightning strike can be disconcerting for passengers. The flash of light, the sound of thunder, and the awareness of being in a storm can lead to unease, and pilots naturally seek to provide the smoothest, most comfortable flight possible. So, how do pilots avoid lightning? Primarily by using weather radar to detect storms that might produce lightning and alter their course to avoid them.
When it's above the clouds, it's fine. It's when it gets down below 30,000 feet, between 30,000 feet and ground, is when you're going to get lightning strikes.
Pilots work with air traffic controllers to maintain an optimal altitude. Despite these precautions, sometimes an encounter with a lightning strike is inevitable. But how do manufacturers ensure the safety against lightning strikes? One of the main protective elements is the Faraday cage. The metallic structure of an airplane forms a Faraday cage around the passengers and critical systems. The cage doesn't stop lightning from striking, but it does ensure that the electrical charge is carried around the exterior of the aircraft and then discharged back into the air, keeping the interior safe. The plane is indeed affected by the lightning, but not in a destructive way. This is due to the conductive structure of the airplane distributing the electric charge, thereby minimizing any direct impact. This is not the only design consideration that helps protect airplanes from lightning. For example, fuel tanks are designed and tested to withstand a lightning strike without causing an explosion. The skin around these areas is made thicker, and all fuel tank vents are equipped with flame arresters. Also, airplanes have devices known as static wicks attached to their trailing edges, such as the wingtips and tail, to dissipate the static charges that build up in the airplane due to air friction or weather phenomena. Now, you might be wondering, despite all these features, couldn't an intense lightning strike cause serious damage? And how do we know for sure that these protective features work as intended?
We want to make sure that our safety is going to protect the plane from those cases.
Boeing, like many manufacturers, subjects its airplanes to meticulous and intense lightning strike simulations to ensure they can withstand the real deal. One essential part of these tests involves a machine known as a Marks generator.
This is a Marks generator. Been around, the concept of it's been around since 1924. So this will generate a 2 million volt arc. So each canister will fire sequentially. So it builds up more and more voltage until it finally has enough to jump all the way across.
Boeing uses this machine to replicate the effects of a lightning strike, ensuring that the aircraft can handle the high voltage. This test has two purposes: to make sure that the airplane's built-in lightning protection is working, and to identify any potential weaknesses in its design. Boeing's lightning protection systems also account for a phenomenon known as a swept stroke, where the lightning channel sweeps across the aircraft due to the plane's forward motion. Boeing's designers ensure that this doesn't cause the lightning energy to enter the aircraft or damage any of the exterior components. The prevention of unwanted arcs is another aspect that designers have to consider.
Sharp points create fields. Fields concentrate the fields around it. Those concentrated fields create a chance to actually jump to another point.
By designing the airplane with rounded surfaces, the risk of unexpected arcing is greatly reduced. Boeing's commitment to safety doesn't stop at just testing and designing its aircraft for lightning protection. There is also constant research and development to find new materials and technologies that can further enhance this protection. As new challenges arise, Boeing is always ready to rise to the occasion. The safety and security of passengers and crew is a top priority in aircraft design, and every thunderous clap of a lightning strike is a testament to the marvels of engineering that keep us safe as we travel across the skies. As you take your next flight, you can relax, knowing that the aircraft is well prepared for any storm it may encounter.